Hi everyone, my name is Elviro, I come from Italy, and I'd like to talk to you about lenses and prisms in Swift. These are functional programming concepts. I'm going to show Swift code, but these things can really be applied everywhere in any language, especially in Kotlin, which is so similar to Swift, or Swift is so similar to Kotlin. These concepts have been around for a while in the functional programming community and also not there. For example, everything started for me with this talk by Brendan Williams, that used to work at Kickstarter. A couple of years ago, did a talk in which he introduced the concept of a lens to the Swift community as basically as an object that encapsulated a way to access data inside a data structure and modify it. And being interested in functional programming myself, I Googled it. And I found this definition, functional getters and setters. Functional here basically means immutable. So getters and setters for immutable data, because when you have immutable data, it's going to be hard to... Getting stuff from your data is easy, but changing the data, it's immutable. So you have to generate new data, and if the thing that we're changing are deeply nested inside your data, it's going to be hard. But I don't think this is really a useful definition, because it doesn't capture the power of the idea of a lens or a prism. I think the main word here is composition. Composition is going to be one of the most said words by me in this presentation. And also, Swift has a nice little thing that are called value types. Structs are value types. This means that when even if you create a mutable struct with mutable properties and you mutate the properties, under the hood, what is really going on is that a new instance is going to be created. So let's see a couple of things about lenses and prisms, things that I think are more interesting. By the way, the reason why lens is called lens is that it kind of allows to focus onto a part of a data structure, a bigger data structure, and manipulate that part. What they do is they encapsulate a relationship between a data structure, okay, and each and every one of its parts. You can have a lens for a part of a data structure. We're going to see this one. But the good thing about lenses and prisms is that they are so simple to define, very small objects, but they offer amazing composition tools. So by this very simple definition and with composition, we end up getting very powerful abstractions. So let's see it a little graphically. Let's assume we have a data structure here. A, B, C, D, E, and F are types. And the ovals can be structs or classes. So the dotted lines are properties. And the dashed lines there are cases, because the rectangles are enums. So let's assume we would like to define a lens on the type A that focuses on the type B. What we have to do is we have to provide two functions. The first function is called get. It's a function that takes the type A, okay, an instance of the type A, and returns an instance of B, so returns the property. It's a getter. The set function is a function that takes an instance of the type B. When we want to set the B, the property, we need to give a new B, and returns a function that transforms the A. So it's a function that takes an A and returns an A. So a lens doesn't care about the fact, you don't see from the outside if the A is immutable or mutable. So it's really good with immutable data, because you get a new version of A that is going to be changed, but this also can be used with mutable data. And as you can see, we define two functions for defining a lens. The prism is exactly the same thing, but for enums. So let's assume we want to define a prism from D to F. This is the way we usually say, lens from A to B. prism from D to F, two functions. The first one is called try get instead of get, because if I want to get the value F from the enum D, well, the D could be in another case. I can get the value F only if it's in the appropriate case. So it returns an optional. It returns an optional F. I get the F if it's the right case. I get nil if it's in the other case. And inject is like set, but when we are injecting something into an enum, we are not we're not changing the enum. We are generating a new one. So the inject is really basically the case function to generate an instance of an enum of a certain case. I'd like to show the code that defines lens and prism because it's so simple. This is the way, the definition that I use. There are many other ways to define. This is the one that I like most. So as you can see, lens is a struct with two generic parameters. The first generic parameter is the whole, so the data structure on which we are applying the lens. And the second is the part. So the part of this data structure onto which the lens is focusing. And as you can see, we just have two properties, get and set. These are functions, okay? So you can define this in any language in which functions are first-class citizens. In Swift, it's the case, so we can just assign them to properties. Prism is very similar. Again, struct with two generic parameters. To see a little better how Prism works, let's consider this enum, for example. This is the view state. It's a generic enum that represents a state of a view, a transitional view, a view that changes over time. And for example, we have the case empty, initial, no data inside the view. Processing, in which maybe we are representing some HTTP request. And it has an associated type, string, because I want to show a message to the user. And of course, the message is going to be put inside a string. And then we have failed and completed. Completed is the generic value, the generic type. So, for example, we would like to define a prism on the processing case. This is going to be a prism in which the whole is, so the data structure is view state T, and the part is the string. So these are the two types, view state T and string. And the processing prism is going to be a prism from view state T to string. Then the try get function of the prism will return an optional string with from this processing prism. Because if we give it an instance of a view state and it's in the processing case, it's going to return a string. If it's not in the processing case, it's going to return nil. And as we saw, the part is the same, as we said before. Part is a string. So if we use this prism, we give it to the inject function a string, and it will return a view state that is in the processing case. So it's really like calling view state dot processing. It's the same function. So this is it. This is the definitions of lens and prism. Let's use this stuff. The main use cases for these things is when you are dealing with some kind of a tree-like structure in which you have structure classes with properties or enums, nested enums at very levels. So a lot of parent-child relationships. And as mobile developers, we work with something like that all the time. It's the view hierarchy, because views have subviews that have subviews, etc. Of course, we prefer to work with a view model, because we don't really like working with views. And I understand that the interpretation, one of the most popular interpretation of the view model is one of a class, an object with state inside and logic. But I am actually talking about something that I could call functional view model, because I'm really interested just in the data. Okay, so my view models are really just a representation of the view as data, so they are structs. And the idea is that we want to act upon this view model, so manipulate our view model with functions. So lenses and prisms are, as we saw, just couples of pairs of functions. Let's see an example. For example, this could be a view model of a login page. we have a title, we have a credential box that is itself a struct that has a username, password fields that are themselves structs called text field with text placeholder and the fact that the text is secure. The button, to login button, uses the view state enum that we defined before, and the generic parameter is set to button. Button is itself a struct, title, and enabled. And for example, we could use this because when we tap the button, we would like to do some asynchronous validation, and so we change the state of the button to processing and show some message to the user. So for example, if we want to add a lens to this thing, for example, to the credential box, we do it, usually we do it like this. We extend the credential box, and we add a nested type that is called lens. But this nested type is really going to act as a namespace. So it's a type with static properties. For example, I define this username field. So when you call this, you call credential box.lens.username field. And as you can see, it's actually the definition of the lens. We are just passing the get and set properties to the lens, the functions. The implementation doesn't really matter in this case because there is only one sane way to write this. And because for my data structure is mutable as all var properties, I was able to just set the username field in the set function. And as you can see, there is only one instance in the entire app of this lens because this is a static property. For Prism, same thing. We extend our enum with another enum that is called Prism. It's going to act as a namespace, and we add our processing Prism there as a static property. The idea is that using lenses and prisms, we would like to manipulate the model. So we have an instance of the model because we are showing to the user our the login page, and we want to do something. For example, we would like to set a greeting title and stored username, and the button maybe is disabled initially, something like that. So we could, for example, represent our initial state as a tuple with the title, username, and the button state. Initially is not enabled. And a way of doing this that's very simple because our model is mutable is to grab a var reference to the model and then set in the properties. Okay. Notice that if the model was immutable, this would have been a mess. Okay, because you had to regenerate the model with all the previous things, but just changing the parts that you needed. This is okay, but it's not that great, really, because, for example, if you see this line, we are setting the text on the username field in the credential box of the login page. So we are basically making three property calls, three nested property calls. And we are not really representing very well the relationship between the login page and the text in the username field. If something changes here, for example, the references to the calls to the credentials or username field change, we have to change this line. But we would really like to encapsulate the idea of accessing the text from the login page in a completely generic way. And this is what lenses and prisms are for. Notice that when we defined the lens and the prism before, actually you define a lens from a data structure to one of its parts. So we probably have defined a lens to the credential box, a lens to the username field from the credential box, a lens to the text from the username field. We would like to compose those things. Can we do that? I mean something like this. If I have a lens from A to B and a lens from B to C, can I create generic lens from A to C, and the same for prisms? Yes, we can always do this, and we can define it completely generically. We don't care about A, B, and C. We could add, for example, a compose method to the lens and to the prism that takes another lens in which the whole is the part of the first lens. And I am not showing the code here again because thanks to the types, the code will almost write itself. There is only one sane way to write this and make it compile. So let's grab some lenses. I can take the title lens. The username text lens is, I get it by composing the 3 single lenses, and the button state lens. Now, to manipulate my initial model, what I could do in theory is to apply the set function of these 3 lenses, one after the other. But I end up with something that is really ugly. It is not really good. What I'm doing here is, the parentheses are not that clear, but what I'm really doing here is that I'm applying the set function of each lens on the old model. I could make this a little more readable with operators, but a lot of people don't like operators, and for a lot of people, they don't really make the code more readable. That's not what we want to do here, because the point is, we have 3 lenses in which the whole is the same, but they are focusing on different parts. So we would like to compose them again. I mean something like this. If we have a lens from A to B1 and a lens from A to B2, I would like to create a lens from A to both B1 and B2, to the tuple of the 2 types. Same for Prism, but instead of both types, we need an either type. So an either is just an enum with a left case and the right case, and it represents either B1 or B2. Can I do this? Yes, I like to call this function zip. It's a static function. I pass 2 lenses there, but I could pass any number. I could write this for any number of lenses. And what it generates a lens in which the whole is the same as before, but the part is a tuple that encapsulates all the parts. And then what I can do is this. I can define my initial state lens. It's a lens that is going to focus on the 3 things that I care about. And then I just apply it. Now I can use the set function. I can pass the initial state, the tuple that I defined in the beginning. And then I applied it to the old model. Notice that the initial state lens, if I give you the initial state lens, what you see is a lens from the login page to these 3 things. You don't see the insides. The lens completely encapsulated the relationships. And then, in a different place at a different time, you apply the new information. So we are kind of separating the relationship between data from the applying of the new information, and so changing the model. What about prisms? Prisms are for enums. So we are probably going to use that to the button state, is the view state that represents the button state. For example, let's assume that our user is logging and the request is processing, but it's taking a long time. So we have a function like this, maybe, a function that changes the processing message. It's just a pure function. It takes the previous message and returns a new one. Nothing, no side effects, nothing. It just changed the message. It's just a little piece of logic. We would like to use this to change our model of the login page. But this is not a pure set, because this is not like we are setting a new message without the knowledge of the one that we already have. We're actually taking into account the one that we have. So we need a new function here, a function that is like set, but instead of taking a part, takes a transformation of the part. Is there a function like that? Of course it is, and it's usually called over. So this function is like set, but instead of taking a part, we'll take a function that transforms the part. And for Prism, it's usually called a try over, because, for example, if we have the processing Prism and we want to apply this function to the function that we just saw, the one that changes the processing message, well, this hover is going to work on the login page only if the button view state is on processing. If it's not on processing, this function here is just an identity. It doesn't care. Okay, it's just going to return the same as before. So we have a lens from the login page to the button state. And then we have a prism from the button state to the processing message. Can we compose those things? Because composing is the point here. We would like to build progressive abstractions that are bigger and bigger, larger and larger, from very small things. Well, unfortunately, there is no way to do this. Lenses and prisms don't really compose well, but don't panic because we don't care. Under the hood is just functions. Lenses and prisms are pairs of functions. I can just grab the functions and I can compose them if I want. By that I mean something like this. I can compose function in a completely generic way. If I have a function from A to B and a function from B to C, I can always generate completely generically a function from A to C. And we usually do this with operators. For example, the dot operator here is just an infixed operator that takes two functions on the sides. And the only thing that it does, it just applies both functions to the argument, one after the other. So again, only one way to write this function for making Swift compile. So here's what we can do. We grab the processing Prism, and then we construct this function on processing by composing the lens over with the Prism try over. And then we get the new model by applying the new processing function to the advanced processing message that we defined before, and then applied it to the old model. Now, if it hasn't already, this is probably starting to look like magic. Okay, so let's unpack this line a little bit. Here, this is what is happening completely generically, but we can actually use the real types here. Because the lens hover is a function that takes a transformation of the view state and returns a transformation of the login page. And the Prism try over is a function that takes a transformation of the string and returns a transformation of the view state button. So as you can see, we have two functions here, and the sides match, the types match. We have a transformation of the view state button on both functions, so this means that we can compose these things. Basically, what we can do, we can simplify the middle part and end up with a function that takes a transformation of the processing message and returns a transformation of the login page. So basically, what this function does is takes a transformation of a very small part and lifts this transformation into a transformation of the login page. And this is what we're doing here, really. We are applying our on-processing function, the one that we got by composing the two overs, to the advanced processing message, the one that changes the message. And then we applied it to the old model. So let's recap for a second. What we did, we separated logic, okay, for accessing mutated data from the actual application of this logic, from the place where we have the information. And to do this, we defined the very simple composable atomic objects. And just by combination, we build more complex object. And the transformation of the data that we applied, we did it with multiple independent pieces that could have been developed completely independently. And the types here are the only interface, because the words that I'm using, lens, prism, get set, over, etc., these are just conventions, really. The types are the thing that matter. The types will make the code compile. So, nothing will break if types don't change. Or is it? I mean, is it possible to write bugged lenses? I could make a mistake in my code. As I said before, if I give you a lens, I'm really just giving you a pair of types. I'm just saying, well, this lens is from this type to this other type. Are we sure? I can assure you that the lens is going to behave. Well, the answer is laws. Okay, I really like this slide. Laws or axioms, okay. Because in software development, we don't frequently talk about laws, but actually they are really important, because every time we want to build large systems from small pieces, okay, we need to trust the pieces. And how do we trust them? Well, actually, in general, when we are writing tests, we are asserting laws. The problem is that usually in unit tests, we assert them implicitly. And this sometimes works, but maybe sometimes if we don't explicit what the laws are, sometimes we end up writing for inefficient tests, or redundant tests. So let's actually define the laws explicitly for lenses and prisms. What are the invariants that must hold for a lens to behave and a prism to behave? Well, for lens there are 3 laws. The get-set law, which means that if I have a data structure and I use a lens and I get something out of the data structure and then I set it back, the data structure must stay the same, must be equal as before. Set-get is the opposite, of course. If I set something into a data structure and then I get it back, it has to stay the same. During the set process, nothing should change. Okay, there shouldn't be side effects or something like that that will change the thing that I put in. And then there is also a law called set-set, which means that the set operation is idempotent. So if I set once, it's the same as if I set twice. Nothing strange is going to happen. For prisms, we have, again, 2 laws, and they are very similar to the one for lens, try, get, inject. If I try get something out of the data structure with a prism and I get it, and it's not nil, when I inject it back, I have to end up with the same enum as before. And inject, try, get is the same. If I inject something, so I reconstruct my enum and then I get it back, it must be the same. Now, how can we test this? Well, we can actually write functions. I like writing functions that are called laws. These are functions that will take a lens, for example, a whole and a part. So an instance of the whole and an instance of the part. And what it does, basically, the function is applies the law, the definition of the law, and returns true or false. So if this function returns true, it means for this lens and this specific whole and this specific part, this law will hold. So how can we test that the lens behaves in general? Well, what we need to do is that we need to call this function a whole bunch of times with different holes and different parts. And we can do this, for example, with property-based testing libraries. What these libraries do is that they will generate random data for me, random hole, random part, with the same lens. And then we call this function, and they will assert that the function always returns true. Like 100 different hole and 100 different part, they call the function. If the function returns true each and every time, I can be reasonably sure that my lens behaves. And I can do this for all the laws. Now, the question is, do we really need to test all lenses and prisms? Because trivial lenses really always have the same structure. We just define lenses for properties of data structure, and they are always going to be the same. Okay, the structure of the get and the set function is always going to be the same. Of course, if I write them by hand, test can be useful because I could make a mistake if I write them by hand. But what I'm really doing here is that I'm writing a lot of boilerplate. So lenses and prisms, defining lenses and prisms for your data types is a perfect fit for code generation. And there is one very popular code generation tool that is called Sorcery. And you can write templates in Sorcery that will generate the source file, the Swift files. And the templates for lenses and prisms are very, very simple. And then I can just annotate my types to tell Sorcery, just generate all the lenses for all the properties here, or the same for enums. Just generate all the prisms for all the properties here. But now in Swift 4, we have, for lenses, a nice new tool that is called the key path. We can actually generate a lens from a key path. Actually, we can do it from a writable key path because we need both the get and the set part. And this function here, this method here, this extension of writable key path, will get us a lens from the root to the value. These are the parameters of the key path. For example, here we have the password lens. So we just use the key path to get from login page to the text, and then we call .lens. But we probably we still want, in many cases, we still want to grab the lenses out of the key paths exactly for those tools that I've been talking about, those compositional tools and the semantics that we get with these tools. And of course, sometimes there are non-trivial lenses in prisms, not just the ones that you get from the properties of a data structure. For example, outputs of combinators. I wrote the compose function, and I said there is only one sane way to write this. Okay, but how can I test that the compose function works? The one way to test this is to see if the lens that I get out of the compose function behaves. And also, sometimes we have particular data structures. For example, I define a lens on a key of a dictionary. So I can focus on the key of the dictionary, and I can get from the get basically will get the value at that key, and the set will set something at the key. I want to be able to test this. How can I test this? Again, by asserting the laws. If I assert the laws with my testing library, and I will be sure, that this lens behaves. One last thing, notice that the line here says that we are generating a lens from a dictionary to an optional value. Of course it is, because maybe inside the dictionary there is no key. That I cannot really focus on that key because the key is not there. So the get part of the lens will return nil, and the set part will remove the value at that key if it's there. But the problem here is that this lens is not really composable anymore, because we have a lens from A to optional B. And how can I compose this with a lens from B to C? Of course, if I wanted to compose this with a lens from optional B to C, this would compose, but it wouldn't make sense. So let's reason about this for a second. Probably what we are going to end up with here is a lens from A to optional C. Of course, the A is okay, but the fact that the B is optional probably means that we are inserting some optionality inside our chain. Well, we could write this function. We could write a compose function that takes a lens from A to optional B and a lens from B to C, and then end up with a lens from A to optional C. It's not that hard to write this, actually. The problem is, and this is what I did in the beginning, I wrote this function. I said, oh, this is easy. And then I tested it. And the test will fail, because a lens generated like this will not respect the set-get law. And it's easy to see how is the case. Because if, for example, I apply this to a data structure in which B is nil, if I try to get a C, I get nil. If I try to set a C that is nil, everything is going to stay the same. But if I try to set a C that is not nil, because I have an optional C, I could set a C that is not nil. Well, this is not going to work, because B was nil initially, but the relationship for B is encapsulated inside the lens. B was nil initially. I don't have anything to set the C into. So the set-get function will fail. So if we want to do this, we really need to inject our B. We need to pass an additional parameter that will inject a default value for B whenever we are using this lens on a data structure in which B is nil. And how can we test this? Well, to test that the lens behaves, of course, we need to test that this lens behaves for any possible B. Again, with our property-based testing library, we can call this function, take the lens, generate the lens, but we need to call this function from like 100 different random Bs, and we need to test that the lens behaves as usual. So, to conclude, I define most of those things in a library that is called Optics. And this is on my company's GitHub organization. And in this library, you can find lens and prism definitions, and also some combinators, some combination tools. But in particular, we are going to find the law functions, so the one that we were talking about. So using these functions, you will be able to, if you define your own lenses and prisms, you will be able to test them against the laws and see if they behave. And that's all I had. Thanks.
Okay, thank you. And so I get it that you're using a lot of function composition, type inference, and custom operators, right? So how do you manage compile times? Do you use a separate target, or is it just fine?
So what I saw is that I have problems with compile times when I use a lot of operators. So I try not to use them. Even with the classic functional programming things, I tend to use methods. Also, type inference is also a thing. I mostly have this problem in closures because sometimes it's a long. It takes a long time to guess the type. So if I see that there is a problem, I explicitly write the types. And you can use in Xcode a flag, a compiler flag. I use it in all my projects, but I don't remember. It's pretty long. It's like dash digbub frontend dash something. And if you use this flag, you can pass the flag a number. It's a number of milliseconds, and it will emit a warning every time type checking a function takes more than that milliseconds. So if, for example, you use the flag and write flag equals 100, if a function in your code base takes more than 100 milliseconds to type check, it will emit a warning. So you can use that to see all the cases. But Swift is not still not perfect in this area. Just don't use too many operators, custom operators, because that thing seems to be very heavy for Swift.
Okay, thank you.
Hey, very good talk. Do you use this together with Eric Swift or something like that, just to transform some like pure functions, transforming some data models? What's your stack around this concept?
So I use these things all over my applications every time I need to deal with data. For example, I don't know, I could use in tests when I have to test if a model is changing in the right way. I use it in Eric Swift because, for example, I have some use cases in which I get some observables of actions, and I transform them into observables of functions that will change a model. And what I do, for example, is I use these things to assert that my actions are the right ones, because usually I represent actions with enums, so I use prisms to get that. And then when I have to transform the thing into something that transforms my model, I compose the lenses that are needed to transform the model, and then I return basically the set function of these lenses. So it will be, in the end, an observable of a function that will transform the model. And I get this function by combining all the lenses and calling the set function at the end. So yes. I think it's fine.
Thank you very much.